Hello everyone, wishing you all a very good morning or good afternoon. I hope all of you are fine, safe, healthy, happy, and doing good. I guess your JEE main results are going to come today, maybe. It was supposed to come yesterday, but it did not come. So we are hoping that probably today or tomorrow the results would be out. Anyways, am I audible and visible to all of you? Can you just wave your hands, raise your hands, tell me that I'm audible, visible? Okay. I see some of you also coming in the regular class. Jyoti comes in the regular class. Bhojaraju, I see sometimes in the regular class. I mean, are you in the crash course batch, or are you from the regular batch? I mean, I see some of you. Even Sudha, I see sometimes in the regular classes. So, are you attending both the classes? Is that so? Or do you have access to all the classes? You are in 11th. You're also attending class for crash course. I don't know. Anyways, in today's chapter, I think we finished yesterday's class with capacitance. We had seen what is capacitance and charging and discharging. We see the formula. We saw the formula. We also saw the relation between capacitor, inductor, and resistance. I told you how they are different and how they are similar. In today's class, we will move on to electric current. Everyone knows what is electric current. Electric current is nothing but the flow of charges. Yes or no? Whenever charges flow, you have electric current. And in the chapter on capacitance, we saw what happens when you connect to conductors. When you connect to conductors which are of different potential, charges will flow until the time when the potential becomes same. Now, if you want to keep the flow of this charge going, you need to apply a constant potential difference between any 2 points in the circuit. And who does this job? This job is done by something known as battery. Now, many a times I've asked students, what does a battery do? And more often or not, I get the same answer, that battery supplies charge for circuit. Battery supplies charge. What do you think battery does in a circuit? Can anyone tell me? What do you think that battery does in a circuit? What do you understand by a battery? What is the function of battery in a circuit? Well, if you think that it supplies charge, that is not the right concept. Charges are already there. These are conductors. Conductors have a large number of free electrons. All of these are conductors. Even resistance is nothing but a conductor. All these are conductors. So they have a large number of free electrons that can move freely. What does a battery do? It creates potential difference between 2 points in the circuit. For example, this A and B. It creates electric difference or electrostatic potential difference between these 2 points. Point A is at a higher potential, point B is at a lower potential, and hence current flows. The conventional direction of current is taken as the flow of positive charges, but we must understand that positive charges do not flow. It is the negative charges, electrons, that flow. So the actual direction of current is from negative terminal of the battery towards the positive terminal of the battery, outside the battery. The conventional direction that we always take is the direction of flow of positive charges, which always flow from a point of higher potential to a point of lower potential. I hope you understand this. Yes or no? I guess you have this much basic knowledge about current. We can start on with our discussion on current. Electric current. What is electric current? Electric current is the flow of charge. Now you can define it in two different ways. One is the average current and other is the instantaneous current. Now this average current and instantaneous current, as you can see the formula, they are of similar nature as your average velocity and instantaneous velocity. Average velocity, if you remember, from our discussion, average velocity is total displacement divided by total time, how much the body has displaced in a given time interval. On similar lines, average current or I average current or I average is the total charge flown through a section divided by total time. So total charge divided by total time becomes your average current, and the rate at which this charge is flowing or in a small interval of time dt, how much charge has flown, that becomes your I instantaneous. I hope you know all this. Then what is the direction of flow of current? Everyone knows the direction of flow of current is the direction of flow of positive charges, which is opposite to the direction of flow of negative charge. Remember, current is a scalar quantity. Why is current a scalar quantity? Anyone can tell me that? Why is current treated as a scalar quantity? Why is current treated as a scalar quantity? Because it does not obey laws of vector addition. So there is nothing very difficult about it. Does not obey laws of vector addition. That is why it is treated as a scalar quantity. Now, whenever we think about current, current is a scalar quantity, but there is a vector quantity involved with current, and that vector quantity is known as current density, denoted by J vector. Now, this is a vector whose direction is same as the direction of current. Direction is same as that of direction of current, but the magnitude is not same as current. It is current per unit area. Do you know this? It's current per unit area. Now, if I want to write it in the form of a vector, how will I write it? It must have a magnitude. It must have a direction. What is the magnitude? What is the direction? What is the magnitude? What is the direction? I have told you that, right? What is the magnitude and what is the direction? So I can write current density vector like this: di by ds. Di by ds is the magnitude of this vector, and n is the direction of this vector. It is in the direction of current. Or I can write di as j dot ds. J dot ds. So the total integral, total current will be integration of this, and that is how you can relate the scalar current to vector current density. Remember, area here is taken as a vector, as area vector. This relation is similar to the relation of electric flux current. If you call current density as electric field, you can define E dot ds as electric flux. You can also think it in that way. I hope you understand this. I hope you understand this small principle. Now, once we have to understand the direct what happens when you apply potential difference. So this is how you will understand it. In a conductor, the electrons are moving randomly. They're moving randomly on possible direction. Their average velocity is zero, and hence current in any conductor, even though it has a large number of free electrons, is taken as zero because if in a particular second x number of electrons are passing in this direction, x number of electrons will also be going in the reverse direction, x number of electrons are going in this direction, x number of electrons will always be coming in the opposite direction, and hence the net flow of electrons is zero, and hence the current is zero. But what happens is when you apply a potential difference or you apply an electric field here, if you apply an electric field across a conductor, the electrons and protons, let us talk about electrons, they start to experience a force which is in the opposite direction. Now, because of this net force, they acquire a speed. That speed is known as drift velocity. It is the average speed or velocity of these electrons along the wire, and because of this drift velocity which is there, because of your applied voltage, a current flows, and the relation is I is equal to N A E V D. Listen to these words very carefully because normally students don't understand this. I standing for current. What does N stand for? N is the number of charge carriers, electrons per unit volume. A is the cross-sectional area. E is the charge of an electron, and Vd is the displacement velocity. Am I clear? Am I clear up till here? Am I clear up till here? So current depends on drift velocity. More the drift velocity, more is the current. More is the area of cross section, more is the current. Charge of an electron is a constant thing, so you cannot change this. N is the number of charge carriers per unit volume. More the number of charge carriers, better is the conductor, more is the current that you will have in the wire. Yes or no? Then we have the famous relation between V and I. There is also relation between mean free path and average time between collision, which is known as the relaxation time. You must know this relation. Vd is lambda divided by t. Lambda is the average displacement of a electron between any two successive collision. That is also known as mean free path. I hope you know this, right? I hope you know this. Now there is a very simple derivation which I think you must be knowing it, where lambda is written in this fashion. Lambda is the mean free path. It is written in this fashion. Tau square time is the average relaxation time. Simplifying this formula, your current I takes this type of an expression. That is the relation between current, area, mass of the electron, and the applied voltage. I hope you remember this. And from here, you can have I is equal to these constant multiplied by V, or I is directly proportional to V, or I is equal to V by R. This entire thing becomes 1 by R or 1 by resistance. And then you have this famous term V is equal to IR, which is also known as the Ohm's law. You all know this. I've already sent you this on your app. You have this sheet on your app. You can go through this sheet. Don't worry. All these formulas are there in the sheet. Okay. Now you must be knowing this way of writing the resistance. Resistance is equal to rho L by A. Rho standing for resistivity or specific resistance, L standing for the length of the conductor, and A standing for area of the conductor. So this is the way you can write this, or you can write E is equal to J into rho. And this is another way of writing the same Ohm's law, right? So remember this, resistance SI unit is ohm. You must be all knowing it. Let us move further ahead into this topic. What you must understand is there might be some questions based on this drift velocity. They normally ask question depending on this drift velocity, depending on the length and area and breadth. So you can just have a look at this table. Dependence on resistance on various factors. So I can write resistance in these two different ways. It is directly proportional to length. More the length, more the resistance. Inversely proportional to area. More the area, less the resistance. It is inversely proportional to 1 by n and 1 by tau. 1 by n means inversely proportional to the number of charge carriers per unit volume. More charge carrier, less resistance, less charge carrier, more resistance. It is inversely proportional to tau. Tau is the average time between collision. If you increase the temperature, average time between collision decreases and resistance increases, and that is how you have this relation. When temperature increases, resistance increases. Can I have some raise hand that we Understand what we have done what we have done till now? Are we all there? Vishnu, Bojraju, Jyoti, Sai, Lusha. Do we understand this better? What we are doing here? Okay. Now, again, some factors, some important point that you must remember on stretching a wire. If you stretch a wire, what happens is volume remaining constant. Length of the wire is changed. Resistance is proportional to length square. Radius of cross sectional is changed because the wire is stretched. So length also changes. Area also changes. Resistance is proportional to L square. Resistance is inversely proportional to R to the power 4. Remember that. Radius to the power 4. Effect of percentage change on length. Now this percentage wala question, remember this percentage wala question can come in the topic of error and measurement. What is the percentage error in the formula for resistance? Is the percentage error in the formula for length or in the measurement of length is falana and all that? So you must remember what? You must remember these relations that I have marked. Then only you would be able to solve any problem on this error and measurement. And error and measurement is one of the topics which JEE Mains and JEE Advanced both are very interested on. So we'll solve a question here. Example, a wire is stretched to increase the length by 1%. Find the percentage change in resistance. How will you do it? A wire is stretched to increase the length by 1%. Find the percentage change in the resistance. All these questions are very simple, but you must be able to understand. Did you get the answer? Do you know the answer? And the answer is right away here. You know the formula of resistance. From there, you can find out delta R by R. Delta R by R becomes delta rho by rho plus delta L by L, all in the numerator, minus delta A by A. Now remember, when you stretch a wire, length increases, but area decreases. And their A into L remains a constant. I hope you remember this. A into L remains a constant because the volume is constant. So delta L by L becomes negative of delta A by A. I hope you understand this. Now, if you understand this, you can get the value of the change in resistance. That will be 0 because resistivity does not change. Plus 1, not plus 1. So the answer is 2%. But again, this is only applicable when the percentage change is very small. Do you understand this? Can I move ahead? Similarly, you must know the formula of temperature dependence of resistivity and resistance. This is the formula. If you put rho, it becomes the formula for resistivity. Alpha is known as the coefficient of resistivity, and T is the final temperature. T naught is the initial temperature. If instead of rho you put R, this becomes the formula for dependence of resistance on temperature. Am I clear? As you can see here, this is the formula now for dependence of resistance on change in temperature. Am I clear? Can I have some raise hand that we are clear, sir? Now remember, this equation that we wrote can also be written in this form, or you can write d rho, small change in the resistivity, is equal to alpha into rho into small change in temperature. From here, you can isolate the terms. D rho by rho becomes alpha dt. You can now integrate this. So this becomes your actual formula of dependence of resistivity on temperature. Remember, this is the original formula. The formula that you saw, the formula that you saw was an approximation. As you can see here, this is the original formula of dependence of resistivity on temperature. If this value is very less, then comes the formula that we know, and that is the formula that I had given you previously. When this value is very less, it can be written in this fashion. Do we understand this? Can I have some raised hand that we understand this, sir? The original formula I have told you, and I have also told you how this original formula is obtained. And we have also seen if the temperature change or alpha into T minus T naught is very less, that formula can be written as rho T is rho naught into 1 plus alpha into delta theta. Do we understand this? Do we understand this? Now remember, the formula that you see is only applicable for small changes in temperature. If the change in temperature is large, we have to use the original formula. It is same as what you heard in Newton's law of cooling. Remember Newton's law of cooling? There are two types of formula for Newton's law of cooling. One is when the change in temperature is very less, you can use the approximate formula. One, when the change in temperature is not less, you have to use the actual formula. What do you mean by that? We'll solve two questions and see how this change, small change and big change makes a difference. These questions are coming right now on your screen. Example number 6. What is this example number 6? The resistance of a thin silver wire is 1 ohm at 20 degrees Celsius. This is placed in a liquid bath and the temperature becomes 1.2 ohms. A change in resistance is very less. What is the temperature of the bath? So how will you find this? Since the change in resistance is very less, we can assume that the change in temperature is also less, 20 degree, 30 degree, 40 degree. That is very less. So you can assume it to be less. Now, how will you find the change in temperature? You can use the original approximate formula RT is equal to R naught into 1 plus alpha delta T. Put it in the equation and you will get the change of temperature as 640 degrees Celsius. Do we understand this? 10, 20, 30 degree doesn't make much of a difference. You can use the approximate formula. Raise hands will give me more confidence that whatever I'm telling you, you are getting this. You have the entire sheet with you. Don't worry. You can always have a look at what we have discussed in the class. Now, look at the next example, which is example number 7. Now, try to understand the difference between the two examples. A conductive wire has a resistance of 10 ohms at 0 degrees Celsius. 1 by 273 per degree Celsius is the value of alpha. Find the resistance at 273 degrees Celsius. Now, here, from 0 degrees Celsius to 273 degrees Celsius, change in temperature is high. Also, the value of alpha is high. So basically what we are looking at is the product of alpha and delta theta. If the product of alpha and delta theta is big, here as you can see, alpha was 10 raised to the power minus 2 and delta theta was 40. So 40 was multiplied by 10 raised to the power minus 2, it was still very less. If this alpha into delta theta, the product is more, you cannot use the original formula and hence you will have to use, you cannot use the approximate formula, you will have to use the original formula. I'll give you a minute. If you can use the original formula and get me the answer. You have to use the original formula in this case and get me the answer. Anyone got the answer? Well, if you have tried, well done. This is how you to do it.
Hello, okay.
You got the answer, beta? This is the original form. R2 is R1 into e raised to the power alpha T2 minus T1. You will get 10 e raised to the power e, 10 into e raised to the power 1. The answer will be 10 times e, and that is the actual value of resistance. Do we understand this? Do we understand this? Can I move further? Okay. Now, electric current in resistance. This is point A, this is point B. Remember, current always flows from a point of higher potential to lower potential. Why do we say this? Because we imagine that current is the flow of positive charges. Positive charges will always flow from a point of higher potential to lower potential. Here, potential of point A must be more than potential of point B. And what is the potential difference between point A and point B? That will be equal to I into R. So that is one way of writing VA minus VB, or you can think it of in a different way, which you will be using in Kirchhoff's law. What will be using in Kirchhoff's law? When you are moving in the direction of current, when you are moving in the direction of current, potential drops. Please mark my words. When you are moving in the direction of current, it is similar to moving in the direction of electric field. The potential drops in the direction of current, potential drops. How much is the drop in potential? How much is the drop in potential from A to B? How much potential drops? The drop in potential is IR. And in Kirchhoff's law, drop is taken as negative, rise is taken as positive. So the drop becomes minus IR. That is what you will use in Kirchhoff's law. Because in Kirchhoff's law, you will be moving in a circuit. You will be moving in a closed circuit. You will be moving across resistances. You will be moving across capacitances. You will be moving across batteries. Whenever you move from higher potential to lower potential, you take it as positive. Whenever you move from lower potential to higher potential, potential rises, you take it as positive. Whenever you move from higher to lower, potential drop, and potential drop is always taken as negative. Potential rise is taken as positive. Do you understand this? In case of Kirchhoff's law, potential rise is taken as positive and potential drop is taken as negative. You all know this. Can I move forward? Can I move forward? Okay. Now in this electric current wala chapter, you will be coming across various type of electrical appliances. You can call them loads. You can call them resistances. You can call them galvanometers, ammeters, voltmeters, light, fan. All these are electrical appliances which are basically a combination of either a resistance or a inductance or a capacitance or a combination of these three. So whatever devices we are using are basically a combination of these three. In this chapter, we are concentrating on resistance. In the topic of capacitors, we were taking all those devices which were only capacitors. In the chapter of induction, we will be taking all those devices as inductors. In reality, all devices are combination of this. Now, whenever you have a device which has a resistance, and remember, you will find it very important in your AC wala chapter. Whenever you have a resistance, some energy is always lost. May not be the case with inductor and capacitor because they can store energy. Inductor in the form of magnetic field, magnetic energy, capacitor in the form of electric field, electrical energy. They can store energy. Resistance does not have that power of storing energy. So whenever current flows through a resistor, whether it is AC or DC, there is always some power or some energy lost in the form of heat. How much is the power or energy lost in the form of heat? Power will be given by VI. You can also write it as I square R. You can also write it as V square by R. How much energy is lost? You just multiply it by T. You will get the energy lost. Remember, this is always lost in the form of heat or sparks or whatever you call it. The only element that consumes power in a circuit is your resistance. Wherever you have resistance, some energy is always lost in the form of heat. Will you remember that? And how much is that energy? If you talk about power, power is VI or I square R or V square by R multiplied by time, and you shall land up with the formula for energy lost in the circuit in the form of heat. Do we understand this? Can I have some raised hand that we understand this? Now, these type of problems are in a lot of demand, whether it's a question for AC or DC. Let us first solve it in DC, because most of the questions that are made for JEE Advanced are made with a practical application, and this has a practical application. This is in DC, you will encounter a similar problem in AC. For bulb rating, please, I want you to understand some terms. So the bulb rating is 100 watt and 220 volts. So basically it is meant to be operated at 220 volt voltage. Here it is DC voltage, or it could be an AC voltage as well. And the power that it gives is 100 watt. This will be given to you. Rating of the bulb is given to you. And then they will ask you a series of questions. What will happen if you do this? What will happen if you do this? What will happen if you operate it at 110 volt? What will happen if you operate it at this, that? If you understand the logic, if you understand the concept, you should be able to solve the question, whether it is in AC or DC. Please mark my words. So solve this question. What is the resistance is the first thing that you must understand. What is the current to the filament? Second question that you understand. If it is operated at 110 volt, then whether you will have less power or more power. 1 minute, think about it. And remember what you understand from this question. One thing always remains constant, and that is the resistance, because it only depends on the material and the dimensions of this material it is made up of. That will remain same, whether you operate it at 110 volts or 440 volts. So first of all, from this power rating is given as 100 watt, voltage is given as 220 volt. From here, power is equal to V square by R. You can calculate the resistance of this bulb. The resistance of this bulb will be 484 ohms. Whether it's a question of AC or DC, it remains same. Can I have some raise hand that we understand this, sir? Many students get confused in this topic. That is why I'm taking it. You don't understand it? Shall I repeat it again? Power, the formula for power applied here is V square by R. The resistance of this bulb becomes V square by P. That will remain constant AC or DC. Now what happens next? They've asked you what is the, when it is operated, what is the current? So you can find out current from V by R. Voltage, you know, it will be 5 by 10 ampere. Now when you operate it at 110 volts, how much power it consumes? It only consumes 25 watt. We have found out the power by V square by R. R remains same. You have changed the voltage. So you see, the bulb was actually having a power of 20 watt, but you are using it at a different voltage on which it is designed, and hence you get less power in that bulb. There might be a question which is asked in a different way, where they have a series of bulbs, sometimes put in series, sometimes put in parallel, different power rating, different voltages. They will put it across one source of power, and then they will ask you in which case which bulb will glow more bright or which bulb will grow less bright. Then you should be able to answer it based on this concept. Do we understand this? Can I move ahead? Remember, this application will be applied in those questions: which bulb will go brighter and which bulb will glow dim. Then whenever you have a battery, I told you what is the purpose of a battery in a circuit. The purpose of battery in a circuit is to give it potential difference. Then you will have something which is known as EMF of a battery. You might get confused with the definition. To get the definition correctly, this is how I define it. This is the negative terminal of the battery. This is the positive terminal of the battery. Outside the battery, charges are flowing because of the potential difference between the battery between the battery terminals. What is causing the charges to flow inside the battery? It's chemical reaction, right? It's chemistry, electrical chemistry. Because of chemical changes that happens inside, because of the electrolyte and cathode and anode. Because of this, what happens inside the cell? Positive charges are moving from negative terminal to the positive terminal. Positive charges are moving from negative terminal to the positive terminal. Some work has to be done in this process. This work done per unit charge is known as the EMF of the battery. Remember that. It is the work done by the battery for the flow of 1 coulomb charge from the lower potential to the higher potential inside the battery. You understand this? This is how we define the EMF of a battery. You can also define it as the potential difference between the two terminals of the cell when the cell is isolated, when the cell is not connected to any circuit. Now there are two types of cell: ideal cell and real cell. In ideal cell, the internal resistance is 0. In real cell, the internal resistance is not 0. I hope you all understand this. Ideal cell and real cell. This is an ideal cell. Internal resistance small r is 0, and hence EMF and potential difference across the cell or the battery are always same. But in case of a non-ideal cell, this E is the EMF of the battery or the cell, and this R is the internal resistance of the battery or the cell. Now, the potential difference across the terminal, if I call this terminal as A and this I call this terminal as B, VA minus VB, this will be equal to E, which is the EMF when the cell is not connected. When the cell is not connected, it will be equal to E. But when the battery is acting as a source or it is getting discharged, this VA minus VB will be smaller than E. When this battery is getting discharged, VA minus VB will be smaller than E. And in the case where battery is getting charged or is acting as a load, this VA minus VB will be greater than E. Do we understand this? So from here you can have the third definition of EMF. It is equal to the potential difference across the terminal when no current is flowing. When no current is flowing, even if it is an ideal battery or a real battery, the potential difference always remains same as the EMF of the battery. Do we understand this? Do we understand this? Okay. Can I have some reason that we understand this? Okay, now there is something which is known as maximum power transfer theorem. Maximum power transfer theorem, we call it maximum power transfer theorem. Now, what is this maximum power transfer theorem? In short, you have a battery whose internal resistance is given as R, and then you have some other things, supplies. All those supplies are known as loads. I told you, any electrical device is a load. Any electrical device is a combination of resistance, capacitance, or inductance. In this case, it is resistance. Every electrical device is a load. Now, there is a simple relation that exists between this internal resistance R an external resistance or load resistance capital R, so that maximum power is transmitted to the load R. Remember, what is our main aim in a circuit? This is my bulb shining bright. I want this bulb to give me maximum power, or this fan to give me maximum power. If it is a DC circuit, what should be the relation between this load and the resistance of my battery, so that this bulb or this fan gives me maximum power? Do you know that relation? Anyone? Have you read about this maximum power transfer theorem, which I call it? I mean, which is the case actually. Anyone knows it? No? Don't worry, I am here. This is the relation between the two quantities. The external load R must be equal to the internal resistance of the battery. And in this case, the maximum power is transferred, and maximum top power is E square by 4R. If I plot a graph between power and the load resistance, this is how the graph looks like. Power is maximum at this point, where load resistance becomes same as your internal resistance of the battery. Will you remember this point, beta? Will you remember this point, beta? Will you remember this point? Can I have some raised hand that we understand this? And here again, as you can see, this curve at 2 points of the load resistance, you will have same power dissipated. If I call this as R1 and if I call this one as R2, there's a relation between R1, R2, and this small r. Now, how it is achieved is, we don't have time for that. We'll just write the result, and the result is like this. Small r square is R1, R2. Small r square is R1, R2. Will you remember this? Will you remember this?
Yes.
Okay. Fine. Okay. Now, let us go around and solve a simple question here, which is based on the concept of this battery and this cells. Find the current in each wire. I mean, the question that you will have in your JE will be of that nature. What is the current in each wire? Now, you will, first question I have is, this wire does not, this here the resistance of the wire is actually taken as 0. The only resistances are given for the cells. This cell has no resistance. The cell in the arm AH has no resistance. Does that make the current infinite in this? So if I've confused you, I have succeeded. Basically, you have to find the current in each of the wires. This wire, this wire, this wire, and this wire. How will you find it out? I hope you know the junction law. Yes or no? You know the junction law? Yes or no?
Yes.
Okay, so tell me the value of resistances in each of the wire. Will you be able to tell me? How will you do it? Okay. Maybe it is difficult for you to understand, is it? Okay.
Sir, KVL we can't apply.
KVL you can't apply. Why you can't apply KVL? What is the problem in not in applying KVL? Tell me. Tell me, beta. What do you think is the problem in applying KVL?
No problem.
Hello? I lost you, beta. What is the problem in applying KVL?
We can apply, sir.
Yes, you can apply, na? So apply, na? Give me the answer. One is 30 volt, the other is 40 volt, the third one is 50 volt. See, beta, there are different ways of solving the problem. What I'll do is first let me go through all these two laws because I don't have that much time. So we'll discuss the problem solving techniques in the next class. Let me just tell you the two laws first so that we can solve the problems in the next one. What is the first law known as? Anyone? Kirchhoff's current law, KCL, right? Or people also known as call it as a junction law. We all understand this junction law? Everyone? No? No one remember the junction law? Now, this point A, where you have two or more currents meeting, is known as a junction. This A is a junction. Now, I am going to call this junction by a different name also. I will call it as node because I'll tell you something known as nodal theorem. We also call it node. So node is nothing but a junction. Now in this junction, what is happening? Some currents are coming in, I1, I3, I4. I've drawn all incoming currents. Not good. So I have to make some as outgoing. How do I make it? Undo. I have to make some as outgoing. Okay, so let us make these two as outgoing. I made all as incoming. Okay, so I made two as outgoing now. This is point A. You can call this point A or junction A also as node. Now, as you can see here, some currents are coming in, I1, I3, I5 are coming in, and I2 and I4 are going out. So basically, the junction law or the current law tells us incoming current must be equal to the outgoing current. So I1 plus I3 plus I5 equates I2 plus I4. We all know this, yes or no? Or sometimes it is stated in this way, sometimes it is stated in this way, summation of current entering a junction is 0. So basically incoming are treated as positive or negative and outgoing are treated as negative or positive depending on how you are taking it. So summation of current is 0 or incoming is equal to outgoing. We all know this. Can I have some reason that we know this?
Yes, sir.
This is known as Kirchhoff's junction law or Kirchhoff's current law, or I call this point as node. Now you can apply the same logic because I'll do capacitance together with this. You can apply the same logic on this being charges and not currents. So if this is the charge Q1, Q2, Q4, Q3, and Q5, what would be my law in terms of charge? If I talk in terms of charge, what will be the law in terms of charge? Incoming charge is equal to outgoing charge, yes or no? So it will be Q1 plus Q3 plus Q5 incoming is equal to outgoing Q4 plus Q5. So this will be my Kirchhoff junction law applied on charges. Incoming charges is equal to outgoing charges. We all agree on this? Can I have some reason that we agree on this? Now I have the second law, which is known as Kirchhoff's voltage law, KVL, or you also call it loop law, because normally it is applied on a loop, but that doesn't matter that you can't apply it elsewhere. You can also apply it on an open loop. Normally it's applied on a closed loop. So basically what does this law say? If you're moving in a loop, the summation of voltage drops, the summation of change in voltage drop across a loop is equal to 0. So basically it is saying that if you move across a loop, the summation of all the EMFs plus summation of all the values of I into R is equal to 0. Do we understand this?
Yes, sir.
Now, in case of EMF, when do we take EMF as positive and when do we take EMF as negative? If I am moving from negative to positive terminal of a battery, if I am moving from negative to positive terminal, the EMF is taken as positive. If I am moving from positive to negative terminal of this battery, it is taken as negative. Do we remember this? Or we were,
Yes.
or you were doing it in a different way? So basically, if I am moving like this from negative to positive terminal across the battery, from negative to positive terminal, I will take it as positive. If I am moving like this, I am moving like this from the positive to negative terminal, I will take it as negative. Do we all agree on this, or we were using some other convention? Now, similarly, for the product of I into R, how will you take it positive? When I move in the direction of current, it is taken as positive. Opposite to the direction of current, this is taken as negative. Do we all understand this? Why it is so? Same logic applies here. So this is the resistance. This is point A, this is point B, and current is flowing like this from A to B. If current is flowing like this, and I am also moving in the same direction, I am moving from a point of higher potential to a point of lower potential. And therefore, if I am moving like this from A to B in the direction of current, the drop potential will be dropping, and hence it is taken as negative because potential rise. I told you, potential rise is taken as positive and potential drop is taken as negative. Here also, in this case, potential is rising. I'm moving from lower potential to higher potential. In this case, potential is dropping. I am moving from a higher potential to a lower potential. In this case also, I'm moving from a point of higher potential to lower potential. Potential is dropping and potential drop is taken as negative. But if I move like this, current is flowing like this, the black one. But I am moving like this from B to A. The way I am moving is from B to A. Then I am moving from a point of lower potential to a point of higher potential. Since I am moving from a point of lower potential to a point of higher potential, potential will be rising and it is taken as positive. I've written it wrongly here, I think. In the direction of current, it has to be negative. I've written it wrongly. Here. So what will I do? How do I erase it? Erase. I've written it wrongly here. So in the direction of current, I've drawn it correctly, written it wrong. In the direction of current, it is taken as negative. Where is my? In the direction of current, it is taken as negative, and opposite to the direction of current, it is taken as positive. Written it wrongly. Am I clear? Anyone has any
Yes, sir.
doubt on this? Potential
No, sir.
rise is taken as positive, potential drop is taken as negative. In case of a battery, from negative to positive, if you move, it is positive. From positive to negative, if you move, it is negative. For resistances in the direction of current, it is negative. and opposite to the direction of current, it is positive. So that is Kirchhoff's current law and Kirchhoff's voltage law. Now what I'll do is I'll just make a fictitious circuit for you, and we will try to apply Kirchhoff's law in this circuit and see how can I apply Kirchhoff's law in this circuit. Okay, so what will I do? I will mark a random point here, A, and I'll assume that current I1 flows here because all is one, I1, I1, I1. It reaches this junction, current will break. Let me call this as I2. So from here, I1 is coming. On the upper wala branch, I2 goes. So whatever comes in the lower branch, don't need to call it I3. Total current is I1. I2 has gone here. So in this branch, it becomes I1 minus I2. I2 is coming from here. I1 minus I2 is getting added up. So total current is I. Now I start to apply Kirchhoff's law from this point. How do I apply Kirchhoff's law from this point? I take the potential of this point as VA, VA, VA. Then I move across this battery. I move from the negative terminal to the positive terminal. Potential rises plus E1. Then I move across this in the direction of current. It drops minus I1 into R1. Then I move down. I am moving in this loop, loop number 1. I am moving downwards. I'm again moving in the direction of current, minus I1 minus I2 into R3. Then I come here, and come back to the same point, VA, VA and VA cancel, and this becomes your equation. This is equation number 1. As you can see, there are two unknowns, number 1 and number 2. Therefore, you need one more equation. You can make the equation in the smaller loop, but I will make the equation in the bada wala loop. So this is my loop 2. How do I make the equation in the loop 2? I again start from point A, VA. I again move across the battery. I again move across the battery. So it is plus E1. I again move across the resistance. So it is minus I1 into R1. Now I move in the upper wala path. I again move in the direction of current, minus I2 into R2. I move across this battery. I'm moving from positive terminal to negative terminal. So it must be a drop. So minus E2. I come here. I move like this. I come back to the point A. It is equal to potential of point A. A and N getting cancelled. This is my equation number 2. Two equations, two variables. You can apply Kirchhoff's voltage law and you can find your answer. Similarly, you can find answers to the question here that I had given. Apply Kirchhoff's law in this loop. You will get the answer for this one. Apply Kirchhoff's law in this loop. You will get the answer for the second one. Apply Kirchhoff's law in the final Barawala loop. You will get the current in this one. I leave you to do this as homework. In the next class, I'll probably tell you a different way of doing it. I'll tell you something known as nodal theorem. Now remember, what we have done today is in this question. See, there were two loops. There were two loops, and hence there were two equations. You have to solve two equations simultaneously to solve this loop, two loops. The method that I'm going to tell you tomorrow, you will be able to solve it in one equation. We'll just make one equation and you will be able to solve this question in just one equation. That we'll be doing tomorrow in the class. Till then, if you have any doubts, you can ask me. I hope you stay safe, healthy, happy. Tomorrow's class, we'll do nodal theorem for current as well as capacitor. Today, I have covered all of what we are supposed to know. Tomorrow, something special coming your way. Till then, take care. Bye bye. If you have any doubts, you can ask me.